So today I want to talk about isopotentials, that is magnetic isopotentials, in terms of pressure gradients. Now, as we all know, Ken Wheeler often says everything is pressure mediation. And this is one of my favorite quotes of Ken Wheeler because it is so true. Okay, it is a very useful way, I believe, of looking at magnetism. And of course, the star of the show is this guy here, which is an isopotential graph that was generated by Michael Snyder's software. It's called Pick2Mag, and I will try to remember to leave a link to his software in the description. But so his software basically calculates the isopotentials, the equal potential in and around a magnet at different levels. And so this guy is what we're going to be talking about. This, I believe, is the magnetic field. This is actually a magnetic field. It is an important aspect of magnetism, and I like to refer to this as the magnetic field. But first of all, I just want to remind you of my definition of a field. I think anyone that uses the term field should really define what they mean by the term field, because there are many, many different interpretations of the word field, and people use it in various ways that can be confusing. So I define a field as a region of the universe. And I generalize the universe because the universe, we could be talking about a large scale magnet, like in terms of galactic size, or a small, scale magnet at the scale of the atom, let's say. And so, so I'm generalizing, so a region of the universe, large scale or small, where each location in the field of view is assigned a physical quantity. So that is my only criteria for calling something a field. If you can assign a value, a quantity, a number to each location in space in the field of view that you're looking at, then I call that diagram a field. A field is a map, a field is a graph, a field is a diagram, a picture, a figure, where each point in this figure is assigned a physical value, a physical quantity. So that's my starting point for talking about fields. So next I want to just review the experiment I did in order to physically measure the isopotential and isopotential around a magnet. And so I received a very nice homemade Gauss meter. This is a homemade Gauss meter that uses a Hall sensor and a little circuit board that hooks into a voltmeter. And what you end up reading from this device is a voltage. And the interesting thing about this is, voltage is a nice analogy between voltage and pressure. And so, when you think about voltage, you can also think in terms of pressure. And so since we are now, in this video, I'm calling isopotentials pressure, I'll be calling them pressure gradients, you'll see why these measurements, these voltage measurements, are exactly what I was looking for. And so, so what I did was, using the Hall sensor, I measured different locations at a certain distance around the magnet. And so what I was looking for, since we're talking about equal potentials, I was looking for an equal voltage reading around the magnet. And so I just arbitrarily chose an 0.06 volts. I think it might have been a minus 0.06 volts, but I chose an 0.06 volts because I wanted to stay on the paper. If I chose 0.05, I might have been way out here and I might have gone off the paper. And if I chose 0.07, so I wanted to kind of make it, pick a voltage that was in a reasonable range to be able to measure them. And so I went around the magnet with the Hall sensor and located the 0.06 volt reading and put a dot there. So I went all the way around the magnet And, I discovered as you get close to the magnet, it's a lot harder to measure, but I was able to measure 0.06 volt readings right up until I got to the magnet. And so, as you can see, these dots match very nicely. The pattern of these dots, the curve that you would draw between the dots fit in very nicely with the shape of the curve of the isopotential graph from Michael's software. And so, basically, if I'd measured down here, I would have gotten a minus 0.06 volts. So on one side of the magnet, it gives a positive reading. On the other side of the magnet, you get a negative reading. Okay, and so the way these lines are plotted is, so the first line here, let's just say, for example, is 0.06 volts, like I was measuring. So then the next line would be 0.07 volts. And then the next curve would be 0.06 volts and 0.08 volts, and then 0.09, and so on. So as you can see, between each of these contours, between each of these curved lines, okay, the potential difference is 0.01 volts. So the potential difference between this pink one and this red one is 0.01 volts. And the potential difference between this red one and this blue one is also 0.01 volts. So as you can see, as you get closer and closer to the magnet, the pressure difference, the voltage difference, is being squeezed into a smaller and smaller space. And so this creates a gradient. This creates a gradient, a non-zero gradient. And this is what I am referring to as a pressure gradient. So what I also want to make clear at this point is that these curves, these contours, are not lines. Okay, they're not lines. They are, in fact, surfaces. So what you're seeing in this diagram here is just the intersection of a plane with a surface. And the surface looks more like this. Okay, and I'm going to show you in real life what it looks like. Okay, so what I did was I generated the first two. I took the first two isopotentials with a potential difference of 0.01 volts. So I took this curve and this curve, this surface and this surface, and I generated a 3D model, which you can see here. Okay, so you've got, and so what I did was I wrapped a surface around each of the surfaces, and infinitely thin because it doesn't have thickness, so it makes it more transparent. And what you can see are the first two, say the 0.06 and 0.07 isopotential surfaces embedded within each other. And of course, there's an infinite number of potentials. It really depends on where you make your measurement, but for the sake of the pressure gradient, basically, I'm showing you the lines where the pressure difference is 0.01 volts. So that is why there are discrete lines being shown here, curves, whatever you want to call them. Contours are the more appropriate term. A contour is a curve that is the intersection of a surface. And there's the surface. So I just wanted to make that absolutely clear that, that although mainstream refers to equipotentials as lines, they are in fact surfaces, and the lines are really contours, which are an intersection of the surface. And so that's a really super important point, and I want to make that absolutely clear that we're talking about surfaces and we're talking about pressure gradients. They are surface gradients. So I just want to take a little step back here and talk about the term magnetic field. So if you go on the internet and you look up the term magnetic field, this is what you're going to find. So what you're going to find is you're going to find the vector field, the flux field. These are lines. These are actually lines. These are lines with arrows, and they're referred to as vectors. Okay, and so this is what you'll find. And the other thing, okay, so let's look at this a little closer. Okay, so again, when you talk about magnetic fields, they always draw the flux lines with the arrows. Okay, they're lines of magnetic flux. This is what they call them. And this is the only graph, the only field diagram, the only map that you're going to find when you do a search for magnetic field. So if you see the other thing that you'll find is that they almost always show you pictures of two magnets that are the same size, the same dimensions, and then the interaction of the flux, what happens to the flux when you bring, say, two unlike poles together or two like poles together of magnets of the same size. And so, as you may have gathered from some of my previous videos, is I'm actually more interested in the interaction of a small magnet placed near a big magnet. And when you do that, something different happens. And so, so this field all of a sudden becomes not very useful for talking about magnets of different sizes. Okay, here again, you've got the flux lines. This is like this cartoon. It's really just a cartoon. It's a graph. It's a drawing. It's a field. It's a field because every point in space, every point in the field of view is assigned a value and a vector. In this case, these lines are vectors, so they're assigned a direction and a scalar, a value, a strength, a field strength. And so this is a field. It's a field, but it is, and although they call it a flux field, flux actually means flow. And so I actually prefer to call it a flow field. The way they draw it is like a flow. They're saying something is flowing from here to here. These are flow lines. Okay, they have direction. Flow has direction. If water isn't flowing, it's got no direction. And so I just wanted to make this clear that flux and flow mean the same thing. I don't know why they call it flux when they could have just as easily called it flow, and everyone would have known what they're talking about. So I think this is more, it obstructs, it's ambiguous, it obstructs the true reality that we're talking about flow. So I wanted to point that out. So as I said earlier, in this video, I want to focus on the connection or the idea of isopotentials as pressure gradients. And of course, Ken Wheeler says all is pressure mediation. And so pressure gradients are a great analogy for this diagram, especially considering that I can recreate this diagram using a Hall sensor that generates a voltage, and voltage and pressure there's a nice analogy between voltage and pressure. So this is why, I'm looking at this in terms of a pressure gradient. So what is a pressure gradient? A pressure gradient is the change in pressure over some measured distance. So here's a picture of a pressure gradient of a weather system. So as you can see, there are, lines being drawn, contours being drawn on this map. Okay, and that this is a map of pressure gradients. So a pressure gradient is the change in pressure over some measured distance. So here you can see the intersection of this pressure gradient, and you can see that there are some lines going through here, and the lines are fairly close together. This would be considered a large pressure gradient. So large pressure gradients imply that there will be strong winds. So strong winds are expected in a large pressure gradient. And so over here, you see that the lines are fairly far apart. And so this would be considered a small pressure gradient. And, in a small pressure gradient, weak winds are expected. And so wind is the flow of air. And so in a high pressure system, the air will flow quickly. And in a low pressure system, the air will flow more slowly. So pressure gradients, pressure mediation is the cause of fast winds or slow winds. So all winds arise due to pressure gradients. Okay, all winds arise due to pressure gradients, and that's what we are seeing in this picture. So now I want to switch to the isopotential graph that I'm showing you here. So let's go back to the definition of a pressure gradient. A pressure gradient is the change in pressure over some measured distance. So over here, you see you have the lines are very close together. So this would be considered a large pressure gradient. So strong flow is expected in a large pressure gradient. And over here, you see the lines are fairly far apart. So this would be considered a small pressure gradient. And in this region, you would expect weak flow. So weak flow is expected in a small pressure gradient. So this is nicely analogous to the pressure gradient of a weather pattern system. So this analogy is, very nice. It's very beautiful, and it's actually easier to explain to people than other ways of explaining magnetism. And so that is the point I'm trying to make in this video. So in terms of pressure mediation, I can say that all flow arises due to pressure gradients. And of course, here I'm talking about the ether. And so in terms of magnetism, flux equals flow. So the terms flux and flow are interchangeable. And so all flow arises due to pressure gradients. Therefore, all flux arises due to pressure gradients. So the implication here is that the pressure gradients that we can measure and see around a magnet are actually the cause of the flow. Pressure gradients cause the winds to flow. Pressure gradients cause the ether to flow. So this is so the flux lines, the flow lines are not the primordial magnetic field. These are potentially the result of the pressure gradient that's generated from the creation of the magnet, the dipole. So next I want to show you a bunch of experiments that I've done personally. Some are remakes of experiments I've done before, and some experiments are new. The point of this exercise is to prove beyond a reasonable doubt the validity and the existence of the isopotential surfaces around a magnet, the pressure gradient as I'm now calling it. So to prove that this exists, and not only that it exists, but it's an important, this is an important map of the behaviors around a magnet. And this can only really be seen when you take a large magnet and a small magnet and put a small magnet near the large magnet and watch its behavior. And so I'm going to prove beyond a reasonable doubt of the existence of this pressure gradient. Okay, so I am still struggling with some people. So there are some people out there that refuse to admit that this is a physical field and that this exists beyond anything mathematical. In fact, some people are even saying that it can't be calculated, even though Michael Snyder's software actually calculates it. So the point of this exercise is to prove beyond a reasonable doubt of the existence of these isopotentials. They are surfaces, but when you intersect it with a plane, they are contours that look like lines, curved lines. And so I want to prove the existence of these surfaces beyond a reasonable doubt. And so here's what we're going to do. I want to put the nail in the coffin of this. I want this to be the nail in the coffin for the existence of the isopotentials. So if I succeed at my goal, I want you to leave a comment and just say you nailed it. So if by the end of this you're convinced of the existence of these isopotentials, then you can leave a comment. But if you just leave a comment, you nailed it, then I will know that you got what I'm trying to do here. So in some of my previous experiments, I didn't have, this is a tabletop. You're looking down at the tabletop, and the tabletop wasn't balanced, and so there was a bit of a bias to the right. Gravity was pulling the magnets to the right, which was actually very useful because it meant that I didn't have to, push the magnet, touch the magnets, or do anything. They just sort of rolled on their own, but they still took the isopotential path. And so that was kind of interesting. But I thought it would be better if I leveled my playing field. And so what I did here was I leveled it, and then I placed a ball bearing in different locations just to make sure it didn't roll to the left or to the right or in any other direction. And so here you can see that the ball bearing is not rolling around, and I can actually push it and it rolls along this line. So I think I leveled it pretty well. So then in the next experiment, you will see that now I can go both ways. So if I can go up this way or I can go up this way, and it follows the isopotentials. So let's just look at that again. So the magnet can go both ways now. So that's all I wanted to level my playing field. And then if you look at one, let's just look at one with the isopotential superimposed, you'll see that it's taking a path that's very much like the what the isopotential surface would look like that intersects the magnet at my tabletop. So the only reason it follows the isopotential line is because it is sitting on a tabletop, and my tabletop is intersecting the isopotential surface at this level of the magnet. And so that's an important point. All right, let's see what I'm doing here. Okay, so yeah, so here what I'm doing is I'm just placing a magnet on the paper. I'm just kind of throwing it there, and you can see it kind of goes this way, and then it turns and it goes this way. So let's watch this. So I just threw it on, and I was trying to throw it this way to try to get it to go the magnet here. See, I just threw it in, and then it just turned and started to go this way. So this, it's basically what I'm showing here is the magnet is going along this path. And then if you look closely, you'll see as it gets close to the magnet, then at some point it just flies to the magnet. So what's happening there, this is sort of a graphic of what I'm seeing on my tabletop. And so each small magnet, of course, each small magnet has its own pressure gradient. And so the pressure gradients, this pressure gradient has to mediate with the big pressure gradient. And once all the pressures are mediated, this magnet wants to sit, this one right here wants to sit here, and then follow whichever potential it happens to have mediated with this big magnet. And so it could be here, it could be here, it could be here. It doesn't have to be on these lines. And these lines are just the 0.01 volt differential between here and here, between here and here, and between here and here. So the magnet can be placed anywhere. It doesn't have to go here, but for the sake of my graph, my drawing, my figure, I'm placing the magnet on the line. So once you place it on the table, it mediates with the pressures of the big magnet, and this of course will point to the North Pole here, will point to the South Pole here, and this North Pole here will point to the South Pole here. And so this is how, what I noticed is the magnets were always lining up such that the dielectric inertial plane lines up nicely with the isopotential. So, and then what I notice is as it rolls along the isopotential surface, when it gets to a certain point, fairly close. So what's happening here is the magnet is getting closer and closer and closer. The small magnet is getting closer and closer and closer to the big magnet. And then when it gets to a certain point, it flies to the magnet. So it looks to me like it takes the isopotential until it gets close enough to the magnet, for the flow of the ether, whatever it is, to get caught into the current or the flow of the ether, and then it flies towards the magnet. So it takes the isopotential when it's far away. Otherwise, it should go straight to the magnet, but it doesn't. It should go, these are the flux lines go this way. These little dots here are basically the flux lines. They're pointing in the direction of the flux lines. You would think the magnet would go straight from here to here, but it doesn't. It goes along here. Okay, so let's just look at that one more time. You can see that it doesn't go straight to the magnet. It curls around until it gets close, and then it flies to the magnet. So that's what I'm trying to depict here. So in this experiment, I'm doing it again, and what I want to show here is how I throw the magnet and it stops, and then it rides along an isopotential. So I'm actually trying to throw it to the magnet. I throw it to the magnet, but it stops, and then it takes the isopotential. So it is stopping here and then going to here. Okay, it's starting here and it's going to here. So I'm throwing it here, it stops here, and then it goes to the magnet. And again, this is what I'm seeing. And in fact, I drew a little more detail here where the magnet is going along the isopotential, then it flies towards the magnet, and then it rolls over to, so sometimes it rolls over to the very middle of the magnet. And so it doesn't just go to the magnet, it's continuously mediating pressures. The small magnet is continuously mediating pressures all along the path until it gets to the lowest pressure mediation, which is this location here. Plus or minus a little bit. It really depends on how it mediates the pressures, but it wants to go here. All right, so in this experiment, what I'm doing is I'm showing you, so I'm going to tap it. It starts to go this way, and then it takes the long way to the magnet. So let's just show, I do that 3 times. So the idea I want to give you here is that, so you got this little pressure gradient here and this big pressure gradient here, and when I tap the magnet this way, all the pressures have to remediate, and for some reason it doesn't want to go this way. It wants to go this way. And so pushing it this way must create a high pressure, and of course, as you know, everything moves towards low pressure, and so the pressures must mediate such that it sends it back along this path. So, and of course, you have to be far away from the magnet for this to work. If I go in this dot here, if I'm in here, it's going to fly straight to the magnet. So it's only outside a certain region that these isopotentials seem to be taking over. So in this experiment, what I'm doing is, what I did was I placed the dielectric inertial plane, this way. So I turned the magnet so that, say, north is here and south is here. And now I am letting the small magnets move towards the big magnet. And as you can see, it always takes this curved path. And so it is basically taking this curved path. When I go that way, it curves in to the left, And when I go on this side, it curls in to the right. Right? So when you're on the left, it curls in this way, takes the curved path. When you're on the right, it takes the other curved path from this way. And basically what these little magnets are doing is they are showing me the physicality, the reality of these isopotential surfaces. It is basically drawing the map. It is following the path of this map, which is a graph, which is a field, mathematically generated field, pressure gradient around the magnet. And so it's pretty hard after seeing this. So if you place it here, it's going to go straight in. If I place it here, it's going to go straight in because all the pressures are mediated in between here and here. So, but if I place it over here, it goes this way. If I place it over here, it goes straight to the magnet because I'm too close to the magnet. But if I place it here, it takes this crazy curved path. So that's the main point I wanted to make here. So in this experiment, I want to show you something interesting that you probably wouldn't know if you didn't play around with the big magnets and the little magnets and the ball bearings. And so what I'm going to show you here, and I left a sound for this video on. Okay. So what I'm doing here is I'm trying to place a ball bearing on the inertial plane, and there I was able to do it. So what's happening here is the pressures between the small magnet and the big magnet are perfectly mediated, and so it can sit there quite nicely. It can sit there quite nicely on the inertial plane because the pressures have been mediated such that it can sit there nicely. But this is not a stable location. All I have to do is touch it a little bit and it flies to one of the poles. And as you can see, it's very difficult. It's very difficult to place this ball bearing on the inertial plane. You have to get it just right. And so there it is. Now I'm just going to tap it. It actually looked like it was a little bit on this side of the inertial plane of the block wall, and so it flies to one side. So if it's just a little bit on this side of the plane, it's gonna, oh, there it flew there all on its own. So if you place it a little bit this side, it goes this way. If you place it a little bit this side, it flies that way. And you can see it just snaps there. It goes super fast. Super fast. Like, it does not want to sit there. It does not want to sit there. It wants to fly from this region here, either up or down, depending on what side of the plane you are placing the magnet. There it is. I found a good spot. I'm just going to touch it a little bit. I don't know what side it's going to go to, but this time it went to this side. And so this is kind of fun to play around with, trying to see if you can actually place it. Oh, there, I placed it there quite nicely. And I'm going to tap it, and it's going to go to one side. So it's hard to really tell when it's on there what side it's going to go to because it's hard to say which side of the inertial, which tiny little bit of side of the inertial plane that it is sitting on. My line is actually fairly thick, and so it's really hard to tell. So I never really know, I never really know what direction it's going to go when I tap it. So that is an interesting experiment. So what's going on here is when you place the small, I just want to do this. I also did the same thing with a small magnet. I did the same experiment with a small magnet. So it doesn't have to be a ball bearing. It can be a small magnet there. I have placed it on the dielectric plane and the inertial plane, and when you tap it, it goes to one side or the other side. And so I'm not going to belabor that too much, but what I want to show you here, what's happening is when you place a magnet or a ball bearing, but place a magnet exactly at the inertial plane, of course, you know, if blue is down and red is up, if south is down and north is up, then north will be down, and south will be up on the small magnet. And so in this sense, all the pressures are mediated when it's sitting right here. So these pressures mediate with these pressures, and these pressures mediate with these pressures, and they're in perfect balance. And so in that sense, I'm able to place a magnet here and let it sit there. But if I just touch the magnet a little bit, if it ends up being just a little bit above the inertial plane, it flies this way. And if it's just a little bit below the inertial plane, it flies the other way. So if it's just a little bit above the inertial plane, the magnet flies up. And it actually kind of spins. It rolls so that eventually, blue has to be next to red, and red has to be away from red. And so the north and the south, of course, have to be together. So over here, south is up and north is down, but it rolls over to here. It snaps very quickly over to here, and such that the south is down and north is up, and that all the pressures are again mediated between the two magnets. And of course, if the magnet is just a tiny bit below the inertial plane of the big magnet, it flies the other way, and of course it rolls the other way, it turns the other way, and such that it eventually ends up here. And it goes there very quickly, just snaps there, like snap, you heard the snap. And so, so this got me to thinking about a famous experiment. Okay, there's a famous experiment called the, I hope I say it right, the Stern-Gerlach Experiment, where they send a beam of silver atoms through an inhomogeneous magnetic field. And what they found was sometimes the silver atoms went up, and sometimes the silver atoms went down. And this experiment was actually near the beginning and was instrumental in the terms for the spin up electron and spin down electron. So, what they're saying is basically there's two kinds of electrons, spin up and spin down, and if the silver atom has a spin up electron, it goes up, and if it has a spin down electron, it goes down. So I may be paraphrasing a bit too much, but that is basically where that terminology came from. And so that got me to thinking about this. So now with the pressure mediation, isopotential surface, and the fact that magnets, first of all, they want to line up with the big small magnet wants to line up with a big magnet. Okay, so the silver atom is technically a small magnet. It's more like a ball bearing, but as you can see, the ball bearing behaved exactly the same as the small magnet. And so individual neutral silver atoms have one unpaired electron, thereby exhibiting paramagnetism. So a silver atom is paramagnetic, which means it's going to be induced by this magnet. Okay, so paramagnetism is a form of magnetism whereby some materials are weakly attracted by an externally applied magnetic field and form internal induced magnetic fields in the direction of the applied field. So basically, this silver atom exhibits paramagnetism. And so like other paramagnetic materials, it is going to behave like a tiny magnet. And very weakly, but because it's such a tiny atom, it's such a tiny magnet, it's going to be more like, okay, we're talking about a small magnet or a ball bearing, if you want to use that analogy, a small magnet near a big magnet. We're going through, in this case, the way they set up this electromagnet, it has to be inhomogeneous, but all permanent magnets are already inhomogeneous, and so they recreate the conditions of a permanent magnet. They send a beam of silver atoms, which are little pressure gradients in of themselves. Okay, they send it through the inertial plane. And then they're surprised when they see it go up and go down. Okay, So the standard thinking at the time was that they should just randomly hit in the middle here, and there should be a blob here. And it turns out that as they go through the field, sometimes they go up and sometimes they go down. And so I couldn't help but think that maybe this pressure gradient might be a better explanation of why the magnets sometimes go up and sometimes they go down. So here is sort of a graphic using my little pressure gradients. And so, you know, let's say the silver atom comes out of the device. So the first thing that's going to happen is it's going to get induced by the big magnet. It's going to mediate pressures, and it's going to immediately align with this magnet. It should, if I understand it correctly, immediately align. The small magnet or ball bearing should immediately align with this magnet, and the pressure gradient should start mediating. And so, or because of pressure mediation, that's why that happens. And then it's going to go through the device, and when it comes out the other side, it's going to get caught in the isopotential as I show in my experiments, and it's going to start to go up. So the pressure, ISO, when it gets further away from the magnet at a certain distance, it's going to move along an isopotential, and if it's above, if it finds itself on the other side a little bit tiny, little bit above the inertial plane, it's going to go up. And if it finds itself a tiny, even just the littlest bit below the inertial plane, it's going to go down. So, so to me, the pressure gradient that I'm talking about, which are the isopotentials, forming a pressure gradient around a magnet, and the small magnet also being a pressure gradient, the behaviors that I'm seeing with my magnetic experiments seem to show that this might be a good explanation for why sometimes the magnets go up and sometimes the magnets go down. Okay. So instead of saying there are up electrons and down electrons, and then when you turn everything left and right, you have to say there are left electrons and right electrons, that kind of language is maybe completely unnecessary if we look at this with a new fresh set of eyes from the perspective of the pressure gradient. So here's another example that seems to vindicate the pressure mediation, the pressure graph, the isopotential graph generated by Michael's software. This comes in the form of a video by Carrie from the Good Vibrations channel. Okay, I want to do a proper review of that video. He recently put out a video, so I highly recommend that you go to his channel and watch his most recent video or more recent couple of videos, because he had a little bit of a breakthrough in his theory, and so I think it would be really great if you guys went to watch this video. So this is just a small point, a small part of the video where he showed, he created, so in his videos he's showing how to create a magnet, and what he did was he created a whole bunch of magnets, and then he was looking at the attraction of the field in this in-between zone. So what he was finding, so he was using a ball bearing, and he noticed that as he added more magnets, the attraction seemed to be weaker in here in this region, but still seemed to be pretty strong on either end. And he also noticed that the ball bearing tended to want to go here and here and here and here, like it tended to want to go into the dielectric plane between a north and a south pole. And so so basically what I did was I took his magnetic configuration and I recreated the isopotentials for this magnet, and sure enough, you do see a smaller, a weaker, not weaker, but a smaller magnetic field. It is weaker in the sense that it is the gradient it's the same gradient, but it's over a smaller region of space. And so, whereas on the ends you have a gradient that covers the same gradient that covers a larger space. And so you can see that in here, the field looks much weaker than out here. This is a much stronger field out here, where the gradient is covering a much region. It has a much further reach. Just like if bigger magnets have a much bigger reach than smaller magnets. So the magnets in here are behaving like much smaller magnets. And so the isopotentials generated by Micro software seem to replicate what Carey is seeing, physically seeing with his experiment. And so I highly recommend, I will try to remember to put a link in the description. If not, please remind me to do that, or just look up the good vibrations on YouTube. Make sure you put that in there, otherwise you're going to end up with a bunch of Beach Boys stuff. So just look that up and you will see he's doing some really interesting stuff, so it's definitely worth checking out. Okay, so I did a couple of more experiments. This is more for interest's sake, and maybe not directly related to isopotentials, but it is related to the behavior of small magnets, and in the vicinity of a large magnet. So here I just have my usual setup with a cylinder magnet. This is just a little wall that I use. I'll explain that in a minute. So I'm taking a medium-sized magnet and a small magnet and placing them on top of each other. And the reason I'm doing this is because I noticed that when I was doing my isopotential experiments where the small magnets were rolling along the isopotential contour towards the big magnet, I noticed that it looked like the small magnet was spinning, and it was rolling. And so, but it was very hard to visualize. And so by putting the little magnet on the slightly bigger magnet, I was able to see this effect a lot better. And I was also able to see something even more interesting. And this is what I'm going to show you first. Okay, so all I did was in this case, all I did was I placed the magnet on the table and it just started to roll on its own. I'm going to play that again so you can see it. I tried to catch it and then I decided not to. I'm like, hey, it's actually going to the magnet. I wasn't really expecting that. So let me go back to that point. And so the reason I put this wall here, I just want to explain that first. The reason I put this wall here is because it's much easier to pick the magnet off the wall than it was to pick, because I'm using a slightly bigger magnet, and it was really annoying to have to try to pull that off the magnet every time. So it was much easier to pull it off the wall than it was to pull it off the magnet. I didn't want the magnet to go flying, the small magnets to go flying to the big magnet every time, and so that's why I put the wall there. It just makes my life a lot easier. See there, it just rolled right to the wall. But it's this resonance effect that I want to show you in this video. You can see how when I place, so what's happening is when I place the magnet, the small magnet set up here near the big magnet, it's trying to mediate all the pressures, and it really wants to line up in it wants the dielectric plane. Let me just go back to maybe this one here. So the small magnet wants to align with the big magnet. It wants to line up, along. It wants to point in this direction of the flux lines, if you want to use that terminology. So it's trying to do that. But it takes some time for it to set up that condition. And so let me go back to this video. Let me go back to this spot. Okay, so when I place, go back to that. So there it is, and it flies to the wall. And then, but now what I'm doing is I'm on purpose putting the magnet far away from its nice resting place. And you can see it vibrates back and forth. It vibrates back and forth, and sometimes for quite a long time. Okay, so there it's vibrating. It's kind of shifting back and forth on its own. That one went for quite some time. And then this one's sort of going back and forth, and then it flies to the magnet. There, I'm just rolling along the isopotential line. But you can see, and I call this magnetic resonance because I believe it's related to magnetic resonance. Okay, so let's just have a look at that a little bit more. So I think the reason, so in magnetic resonance, MRI, magnetic resonance imaging, right? What they do is the hydrogen atoms that they resonate with the system actually kind of processes. So it doesn't wiggle back and forth necessarily. It, like you're seeing in this experiment, it is actually precessing. So, but because this setup is confined to my tabletop, is confined to a plane, it is wiggling back and forth. But I think if it didn't have that constraint, it would actually precess. It would kind of turn around, just like they say the hydrogen atoms do in magnetic resonance imaging. And so, I think what I'm seeing here is literally identical to magnetic resonance, which is why I have the title here, magnetic resonance. So it is resonating and then it finally winds down. So in magnetic resonance imaging, they resonate the hydrogen atoms, and then when the atoms wind down, that's when they do their imaging, because it is creating an effect. It is creating an effect that they can measure. I'm not going to get into the details. If you want to look up magnetic resonance imaging, you can, and then you can look at this experiment and see how it could be related. Okay, and so here's another experiment. This one is very cool. This is actually, I wasn't sure what to expect here, but this was very interesting. So here we've got, I measured the South Pole. So in this experiment, the South Pole is up on the big magnet. Okay, the South Pole is up. So we're on a tabletop, but we're looking down at, like all my experiments. Okay, I just put the wall there so I don't have to pick the magnet off the magnet every time. So look, you can see that the small magnet appears to be spinning clockwise. So with the two magnets, I was able to see, with the two magnets, with the one on the other, I was able to kind of see the spinning that was hard to see with just the single magnet. Okay, you can see it is spinning. I'm going to go back a little bit here. Okay, let's have a look at that. So again, I just wanted to show you that that's the North Pole. The North Pole is up, and you can see that it's spinning and it's precessing as it's spinning. So it looks like it's spinning clockwise, but it's orbiting counterclockwise. So it's orbiting this way. It's taking this path, okay? But the little magnet is actually spinning all on its own. I'm not spinning it. As soon as I put it down, it just starts spinning. Okay, I'm just dropping it and it just does its own thing. It's spinning on its own. Okay, I just placed it there. It stopped for a second and then it started spinning. So here's a close-up of it. Look, it's spinning clockwise and it's moving in the direction. Right, let's have a look at that again. There, it's spinning clockwise. So you can clearly see it's spinning clockwise. Now I'm going to reverse the magnets. Now I'm going to put north up. So north is going to be up. And the other magnetic setup is going to have south pointing up. And the reason for that is because north attracts south and south attracts north. But here, now you can see that these small magnets appear to be spinning counterclockwise, and they're precessing because there's a little bit of an imbalance between the medium magnet and the small magnet. So let's have a close-up of that. So here I was able to place it down and not have it spin. So I was able to mediate the pressure so it doesn't spin. But then if I just tap it a little bit, it starts to spin. It's spinning counterclockwise. It's spinning counterclockwise, and it's following more of the isopotential path. It's not going straight to the magnet. It's spinning. This is spinning counterclockwise and going up the other side of the isopotential. Okay, so anyway, so that's about it as far as the experiments go. So the goal of this exercise was to prove beyond a reasonable doubt that the isopotentials that I'm talking about here, that I physically measured. So let's do a little review. Okay, so the isopotentials that I physically measured, that's one piece of evidence to show that the isopotentials are real, because I was able to measure them with the Hall sensor. Okay, I was able to measure them with the Hall sensor, and I just measured one set of points just to prove that they do in fact take on the shape of the isopotentials that are calculated by Michael's software. Okay, so and of course I refer to them as pressure gradients, and I do a bunch of experiments, you know, this one here where I show the magnet going along, taking the path of the isopotential. Of course, I tapped it in that direction, but that doesn't matter. I could, you know, I could just place it there. I did many experiments where I just place it there, like, or just give it a very light tap, and it takes it just goes on its own toward the magnet. Okay, so in this experiment, right, I show how I kind of throw it at the magnet, but it still takes. So I'm trying to make it go toward the magnet, but it instead takes the isopotential path. I can see the isopotential path with my own eyes. It is taking that path. And then when you look at it from the orthogonal path, let's just go in a little bit here. Okay, if I place it over here, it goes in this way. And if I place it over here, it goes in, it takes this path. Okay, place it over here, it takes the curved path. It takes this curved path. So with looking at this experiment alone, I can literally see, the magnet following this isopotential path. And the reason it does it is due to pressure mediation. Okay, so you know, and then there's this experiment where I show that when you place a magnet or a ball bearing on the magnet itself, that it flies towards the North and South Pole. So, or I can sit it right on the dielectric inertial plane, and then when you touch it, it flies to the North and South Pole. And so basically what we're seeing here is the two pressures being mediated, and that there is a huge force forcing this magnet to this position here through the pressure gradient mediations. And then I showed you quickly that the isopotentials could be a nice explanation for this experiment, which was historically attributed to spin up and spin down electrons. And so that's about it. Ken Wheeler is right. Everything is pressure mediation. And I am right. I believe that this isopotential surface diagram is a great depiction of the behaviors around a magnet. It tells me a lot more, in my opinion, it tells me a lot more about how a small magnet is going to behave in the vicinity of a big magnet, much more so than the flow diagram, the flow lines. This diagram doesn't give me any clues whatsoever as to how a small magnet is going to behave in the vicinity of these flux lines. So these flux lines does not give me enough information to tell me that something special is going on here. Okay, something special is going on here. Something special is going on here. Okay, all the pressures are mediated. This creates a low pressure zone, right? This creates a very strong attraction between a north and a south pole, whether it be a single magnet or a bunch of magnets. And so that is, I'm going to leave it at that. I'm just going to show you one more time this isopotential surface diagram, just because it looks really cool. And I just want to zoom in on this and show you, if it will let me, is right here, right between these two beautiful, beautiful pressure gradient surfaces, right? This one and this one and the inner ones. Anyways, I think this looks really cool. I like it a lot. And so all is pressure mediation. All is pressure mediation. So if I convinced you beyond a reasonable doubt of the existence of the isopotential surfaces, aka the pressure gradients that appear to be around a permanent magnet, then I would like you to leave a comment in the comment section, and I want you to say you nailed it, because the purpose of this video was to put the nail in the coffin of this debate that I seem to be having with some people, that this field, that this diagram, that this figure has physical meaning beyond a reasonable doubt. So just say you nailed it, and I will know that you got my message. Thank you very much. Have a great day.